here is our population that we're going to sample from. That's why it says parent population. So we'll start with a normal population, has a mean of 16 because it's normal. It's also its median is 16. Population standard deviation of 5, and because it's perfectly normal, skew is 0, kurtosis is 0. Now, let's try something out here. Down here, I'll have this set to mean, which is the sample mean, and it'll be from a sample of size 5. Now, I know we use the little letter n for sample size, but they're using capital N here. And I'm going to also down here set this to mean, but it's going to be set to a sample size of 25. Now I'm going to click on this animated sample. Let's see what happens. There's a random sample of 5, then a random sample of 25. Let's do that again. Sample size 5, sample size 25. Now, which do you think is going to produce a better sample mean? A sample mean that's going to be a closer estimate to this population mean of 16. A random sample of 5 or a random sample of 25? Well, you probably think, gosh, I got more information here, so that should produce a better sample. Now, we would like to repeat this process many times. Repeated sampling, and then look at the distribution of all the sample means we would get from that repeated sample. We can speed things up here. If I click on this 10,000 samples button, it'll take 10,000 random samples of size 5, calculate the sample mean, and plot the distribution of all these sample means. I'll also do the same thing down here, but those 10,000 samples will be of sample size 25. And then I'll get the resulting sample means plotted here. Let's see what it looks like. Oh, that didn't take long. Let's get 100,000, why don't we? I'm just clicking on this 10,000 samples button. Important to remember, don't click on it again until it's done here, otherwise you'll mess it up. You'll know you messed up if you get a standard deviation of 0, because you know that's not possible unless all the data values are the same. That's obviously not the case here. Let's see, we're up to 70,000. Let's go up to at least 100,000. Now that's a lot of sample means. So here we've got 100,003 sample means. You can see that they're clustering around the population mean here of 16. The sample mean is an unbiased estimator of the population mean, meaning it doesn't overestimate any more than it underestimates. So if you take the average of all these sample means, it should average out to the population mean of 16. And we can see it's very, very close. Now, what happened down here? Once again, looks like it didn't overestimate it anymore, it underestimated. So the average of all these sample means should be very, very close to 16. Ooh, it is, right on. So both of these sampling distributions for the sample mean are normal. So you look at the skew, kurtosis, very, very close to 0. So they're both normal, have the same mean. That means there's only one other way they can vary, and you can see it, I think. And that's in their variability, or their spread, the variation in the sample means. And it makes sense. These sample means came from larger sample sizes. So those sample means were better estimates, and look how much closer they're clustered in to the population mean. These are clustered around the population mean, but not as tightly, not as closely, because they were a smaller sample size. Now, here's something we could check. The thing with sampling distributions for the sample mean is the mean of all the sample means should be equal to the population mean. So that's easy to check. Population mean is 16. The mean of all these sample means is very, very close to 16. And this is right on. So that's true. But notice the difference in spread amongst all three of these. let's get our calculator over here and scoot this over here. And how it's supposed to work is this. Is if you take the population standard deviation of 5 and divide it by the square root of the sample size, it should equal the standard deviation for the sampling distribution. Well, here we had a sample size of 5. So, what answer do I expect when I hit enter here? Well, it should be close to this 2.24. Don't expect to be exact, just close. Hey, that rounds off to 2.24. So yes, it appears that the sampling distribution spread is equal to the population standard deviation divided by the square root of the sample size. So let's check it with this one down here. Let's take this population standard deviation of 5 divided by the square root of our sample size at 25. Now, what do I expect the answer to be? Should be pretty close to this 1 here, which is the standard deviation for this sampling distribution. Yep, sure enough. So this is reassuring us that it really does seem to follow that formula. That you can see the larger your sample size gets, the smaller the spread or variability in your sample means. So they cluster in more closely. Well, this is all well and good, but let's look at the central limit theorem in action. Now, this is the biggie in statistics. This just changed everything once this was discovered. Now, I can go down here and select skew. Now, that's pretty heavily right skewed. Now, before we had the central limit theorem, we were stymied. We couldn't work with populations like this. We had to have normal populations. But then we made a discovery. Because our statistical methods are based upon the sampling distribution being normal. So we don't care about the population if the sampling distribution is normal. Well, here I'm going to do the same thing again. Take random samples of size 5 here. Random samples of 25 here. Let's just click on animated sample. There's the 5 and the 25. Why I like you to click on the animated sample when you do this, it really reinforces the difference between these two. You see how many more data values are being put into each sample mean for this one as compared to this one that's only getting 5. That's kind of pathetic, doesn't it? Sample size of 5. Now that you've seen that and you can visualize this concept of repeated sampling, let's pick up the pace a little. Click on 10,000 samples. Notice I don't click until it's done. You can see once this is incremented by another 10,000, it's safe to click on this button again. There we go. Now, do these look as heavily skewed as the population? Heck no. Now, this one definitely has a tail here, so you can see it's overestimating more than it's underestimating. So the mean gets pulled towards the tail, and so we can see the mean is a little bit bigger. It's not too bad. It's nothing as extreme as with the population. Look how much bigger that mean is to the median. You can see how much farther it got pulled to the right. And so looking down here, you can also look at the measure of the skew. Remember, the closer it is to 0, the more normal it is. So you can see that the sample means from the larger sample size of 25 has less spread. They're scrunched in closer. And it's more normal. It's not as skewed. There's a little right skew there. You can see that here in this positive value. But it's not too bad. So now here was the huge discovery. That as your sample size gets bigger and bigger, the sampling distribution becomes more and more normal. So that was a huge discovery, because our statistical methods will work if our sampling distribution is normal. And so we realized all we have to do is make sure we get a large enough sample size. So how big does it need to be? Well, what I'm going to give you is just a general guide. And that guide is, that most statisticians agree with, is if your sample size is at least 30, so 30 or more, then it's reasonable to believe that your sampling distribution is normal. Now that's just a guide. 30 is not a magic number. For example, I could make a really wicked one here. Let me go down to custom, and I'll make something really, really, really skewed. Now that one's pretty nasty. Look at the difference between your median and mean. And you can see a big positive skew. That's really, really skewed. Now, as before, we can repeat this process. I'll go ahead and get 100,000 here. There we go. Now, if you happen to have a population that has got a really nasty skew to it like this one, probably a sample size of 30 is not going to be big enough. But that's an extreme situation. So that's why I'm telling you sample size of 30 or more is just a guide. It will usually work just fine. But don't expect it to be a guarantee by any means. See, the central limit theorem is just telling you that the larger and larger your sample size gets, the more normal it gets. So getting the largest sample size you can afford to get, the better. But this 30 or more is your guide. All right? Oh, and as before, let's go ahead and check those rules. Does the mean of our sample means equal the population? Well, this is 7.93. Is this one close to 7.93? Very, very close, as is this one. So even though these things, these sampling distributions, aren't exactly normal, the mean of all the sample means is still very, very close to the population. In fact, this one's right on. How does that spread? Does that still hold? Well, let's check it out. Now let's hit clear there. Now we've got a population standard deviation of 7.9. Let's divide that by the square root of the sample size. For this one, that's a sample size of 5. And hit enter. And is this close to this? Pretty close. It's not exact, but I wasn't expecting exact, but it's still pretty close. That's all I was hoping for. Let's try this one down here. Take our population standard deviation, 7.9, and divide by the square root of its sample size, 25. Hit enter. Now, 1.58, is that close to what I was expecting? It sure is. So what I'd like you to do is play around with the Java applet. You saw this movie, so you know what to do and how to use it. And it takes time for this concept to sink in. For example, like when you take the first time you're sampling from here, your observational units, the individuals you're looking at, are the individual data values. But then when you create here, now the observational units are the samples themselves. And what you're taking from each sample is the sample mean and plotting it here. So you see there's 2 levels to that. So you need just some time to let that sink in. And you've got this Java applet to help you visualize the process. And it's real important you do. This is the foundation of inferential statistics. What I always like to say is, the reason statisticians absolutely love the central limit theorem is they wouldn't have a job if it weren't for the central limit theorem. This is what makes inferential statistics possible. This is what ensures that our sampling distribution is normal, so we can use the statistical methods. Okay, that's it for this lesson.